All right, so let's go over this. Like I said, this wasn't a required thing for the quiz. I just kind of wanted to see how much of the fluid and electrolyte book you guys have been reading and kind of how you're doing. Well, we'll go through this. So, first of all, let's just define a few concepts. How does that sound? Okay. We'll start there. Actually, this is kind of cool stuff. It's actually really cool stuff. So let's define a couple of concepts first. So what I want to do is I want to just go back to that chemistry that we talked about. When you get into class, do you guys remember any of that? Yeah.
The what?
The chemistry? Yeah, the what? So I want to go back to the concept of a mole. Alright, a mole. Okay? And do you guys remember what a mole is?
It's like a 1,000 cubed or
What's a number?
6.02 times 10.
Yeah, it's a huge, huge number. It's Avogadro's number, 6.02 times 10 to the 23, I believe, right? All right. 6.02 raised to 10 to the 23. So there are a lot. This decimal point's going to move over many, many times. Okay. So that's what a mole is. And if you remember, we talked about chemistry when I looked at an element, like hydrogen, for example. Every element has an atomic number, which is the number of protons, right? And every element has an atomic mass as well. Hydrogen, I just have it off the top of my head. It's easy. It's 1.001. So it has an atomic mass of 1, basically. And the really cool thing about this Avogadro's number is, whatever the atomic mass is of the element, if I have Avogadro's number of that element, of that atom, I have that many grams. So if I had 6.02 times 10 to the 23 atoms of hydrogen, I would have 1 gram of hydrogen. So 1 mole of hydrogen would be 1 gram. Helium has an atomic mass of 4, so 1 mole of helium would be 4 grams, and so on and so on. So mole is a really critical concept for kind of turning the world of atoms into the world that we know, the tiny world of atoms into the bigger world that we know. Well, what we can do is we can take this concept and we can apply it to physiology, to labs in particular. So when I look at measuring stuff like dissolving solutes in blood, for example, because that's kind of important, right? Would you guys pretty much agree that looking at dissolved solutes and solvents, particularly in blood, it is kind of important. And one way of measuring the stuff that I have in my blood is through what's called molarity. Molarity, okay? And molarity is just simply the number of moles of whatever stuff I'm measuring, sodium, chloride, potassium, proteins, whatever, moles in liters, moles per liter, okay? So if I had 1 mole of sodium, for example, the molarity of sodium would be 1 mole per liter. Does that make sense? Everybody's okay there? Okay, so I have 1 mole per liter, but remember when we talked about mole is kind of a big number, isn't it? So what we can do is we can kind of break that down into a millimole, which is 1,000th of a mole. You guys remember that? A millimole is 1,000th of a mole. So 1 1,000 of a mole is 1 millimole. Okay, so 1 millimole per liter. And we often measure molarity in the body in millimoles per liter. Does that make sense why? Because moles it's such a big number. Okay? But a millimole is just simply 1,000 of a mole. Everybody's okay there? That's molarity. However, in physiology, we tend to measure something called molality, which is what I was talking about on the quiz there. Is there a difference between molarity and molality?
Oh, I'm sure there is.
There is. It's really subtle too. Okay? So molality is moles, not per liter, but moles per kilogram. Okay? Moles per kilogram. Okay. Somebody's getting a text message, I heard it.
Sorry about that.
No, it's alright. So we have moles per kilogram. This seems like a huge difference, doesn't it? But here's the cool thing. In the human body, what is the most significant solvent? Water. Here's a question for you guys. 1 kilogram of water is how many liters? 1 liter. 1 kilogram of water equals 1 liter, right? And I know this because I know the density, okay, this P rho, that's just an abbreviation for density. The density of water is 1 gram per 1 milliliter, okay? So if I had 1,000 milliliters, I'd have 1,000 grams or 1 kilogram. So in physiology, okay, in medicine, we typically use molarity and molality kind of interchangeably, even though there is actually a slight difference when we start talking about the solute that takes up a certain amount of weight. In medicine and healthcare, these are more or less the same, okay? Is everybody okay there? They're more or less the same, but it can become significant when the solvent isn't water and when we're talking about outside the human body. But inside the human body, these are more or less the same, okay? Moles per kilogram, again, 1,000 of a mole is going to be 1 millimole per kilogram, and so on and so forth. Everybody's okay there? But we know that 1 kilogram of water is going to be about a liter of water. Everybody's okay there? So really, they're more or less the same in medicine. That's a big thing there. Okay, we're good there. So, what we do is we can also measure in something called osmols. Okay? Osmols. And what did you guys, when you read about osmols, did you read up a little bit about the concept of an osmol versus a mole? What do you guys think? An osmol? It's okay. Again, it's pretty subtle what the difference between a mole and an osmol is. Okay? An osmol really is dealing with how something that dissolves in water actually acts like, how it acts. So, for example, if I have 1 mole of sodium dissolved in a liter of water, I have 1 mole per liter, or 1 mole per kilogram, more or less. How does sodium act when it's dissolved in water? So does it act like a single particle? No, just sodium, not sodium chloride, just sodium. Does it act like a single particle? What do you guys think?
Yes.
Yeah, it acts like a single, it's just sodium, right? It's just 1 particle all by itself. It's just 1 particle. So we could, when sodium acts like 1 particle, 1 mole of sodium is going to be 1 osmol. Okay? Because when I dissolve that sodium in water, it acts like 1 particle. Does that make sense? But now let's say that I have 1 mole of sodium chloride, and I dissolve that in water. What's going to happen? And you guys have kind of started mentioning now. Yeah, this particle of sodium chloride doesn't act like 1 particle in water, does it? It ionizes into 2 particles. Does that make sense? So 1 mole would actually be 2 osmols because it's acting like 2 particles. Does that make sense? That's all that osmol is. Osmol is dealing with how does something act when it's in water. Okay? Does that make sense? That's all it is. That's all it is. That's why we call it osmol. Os being, of course, water. Okay, so when we talk about measuring the osmolality of the blood, what are we talking about? Yeah, we're talking about dissolving stuff in blood, and how does that stuff act? What, right? That's all we're talking about. Okay? We're talking about osmols. Particularly, we're talking about milliosmols, right? Because again, an osmol is a big number, so we break it down to osmols. Okay, so is everybody more or less okay there? Does that kind of make sense? What's going on there? All right. So osmolarity or osmolality is looking at the blood and looking at all the dissolved stuff in the blood. Is everybody okay there? And I have a certain amount of dissolved stuff in my blood, and that stuff can be measured in milliosmols per liter. Is everybody okay there? Does that make sense? Okay, so let's throw a monkey wrench in there. Let's throw a little monkey wrench into that. Why in the heck? What's up with the milli equivalents then? What's the difference between milliosmols and milliequivalents? Nothing. I like that. That's a definitive answer there.
And he's so confident about it.
Huh? Yeah, sometimes the right answer. The difference is it's, again, kind of subtle. It's very subtle. It's kind of like the difference between molarity and molality. So when I talk about milliequivalents, first of all, when we measure something in milliequivalents, that something has to be what? It has, huh? Well, it's in a liquid, yeah, but there's something very special. So when I measure sodium, for example, I can measure sodium in milliequivalents, right? You're on the right track. I can measure potassium in milliequivalents, right? Could I measure glucose in milliequivalents? Okay, you're kind of on the right track. Have you ever seen glucose measured in milliequivalents? No, it's milligrams per deciliter, milliosmoles per liter. We cannot measure glucose in milliequivalents. Why is that? And, well, you're on the right track. Right there, when you said polar, you're like,
Polar and bipolar, like the
you're right there when you said polar. You just have to take a clip. Just jump off the cliff. Just jump. Just do it. Just do it. It has to be, if you're polar, you're what? Charged. It has to be a charged something. It has to have a charge. So sodium can be measured in equivalents, right? Potassium, chloride, bicarb, all of these have charge to them, right? They're charged. Glucose, however, not charged, right? So we can't measure that in milliequivalents. So that's the first thing. A milliequivalent, an equivalent, if you remember talking about equivalents in acid-base, an equivalent is, one mole of a charged substance like sodium, for example. 1 mole of sodium per liter. Does that make sense? But I couldn't have an equivalent of glucose because glucose is not charged. So does that make sense? I know it's really subtle, because I could take glucose and I could have one osmol. I could have one osmol per liter, or 1 osmol per kilogram of glucose, right? And I could have 1 osmol of sodium, but I could not have one equivalent of glucose. Does that make sense? That equivalence is specific to charged particles, and millimoles and milliosmoles, osmolarity and osmolality, looks at the solution as a whole. So it looks at the blood as a whole. Milliequivalence is what we use to measure tonicity. And when I'm measuring the tonicity of something, hypotonic, isotonic, hypertonic, what am I really looking at? Am I looking at just one thing when I'm measuring tonicity? I'm looking at 2 things, right? I'm looking at 2 compartments separated by a membrane. Okay, so when I measure the tonicity and I'm looking at milliequivalence, I am more interested in, okay, let's call this compartment A. That's outside of the cell, that's extracellular, and this is compartment B, that's intracellular. And I'm more interested in the difference in tonicity, right? Or the difference in milliequivalence in each compartment. Does that make sense? So tonicity, iso, hypo, hypertonic, is measured in milliequivalence, or equivalence, but milliequivalence is in the body. And it is more interested in looking at the difference in concentration between 2 compartments that are separated by a membrane. Osmolality and osmolarity doesn't care. It's just looking at the blood. Does that make sense? Everybody's okay there? All right, so now that we have a reasonable foundation built up, let's now talk about the serum osmolality and the osmolol gap. So the osmolol gap, okay, the gap is, the general formula for the gap is what? Be measured, subtract mine or less the calculated, right? So what happens is when I run my chemistry, my blood chemistry, I can have the machine measure the osmolality. Does that make sense? So the measure is not something that I can calculate the formula. It actually has to be measured. But then what I do is I calculate the osmolality. And the measured and the calculated should be pretty close together, right? Would you guys agree? That what the machine is measuring and what I'm calculating should be pretty close together, right? Well, let's talk about how we calculate. Okay? There is a formula that we can use to calculate the serum osmolality. What do? Well, we look at the major players that are dissolved in the blood. Okay, so what are the major players?
Sodium.
There's sodium.
Your BUN or your urea.
Yeah, your urea or your blood urea nitrogen. That's a big, not really a big molecule, but you have a lot of it. It exerts some weight. So you have your sodium, you have your BUN, and you have your glucose. Everybody's okay there? More or less? And then, yeah, we'll talk about that a little bit. Okay, but I can't just add these together, right? Because sodium's charged, BUN, and glucose is not charged. I have to do some math to my values. There's some coefficients, and I have to get all my values in the same units and talking the same language. So some of them I have to multiply, some of them I have to divide, and that's to get basically, if you want to think about it, these 3 guys are kind of speaking different languages, and you kind of got to get them all on the same playing field, speaking the same language. So what do I have to do to the sodium?
There were different formulas. It was,
Okay.
I found.
Sodium, well, multiply by something. What's the common one? Multiply by something.
Either 1.86 or 2.
2, yeah. 2 is generally what we go with. Okay, what do I do with the BU and I have to divide it by something? No, I'm not dividing it. Say again.
2.8
18?
and 2.8.
18 or 2.8? What do you guys think?
Glucose is 18.
Glucose is 18, right? You sure?
Yeah.
Yeah.
Yes, there you go. So glucose is divided by 18, and BUN is divided by, say, 2.8. There we go. Yes, glucose we divide by 18, and BUN we divide by 2.8. And doing these operations with these coefficients gets all these numbers on the, gets them speaking the same language, if you will. All right?
Where does the 2.8 and 18 come from? Like, where is the reason that those?
I could show you. It'd take a little while.
That's not it.
It would take a little while. It's actually, once I show you, it's actually not that mysterious. But, well, for example, let's start. Sodium's easy to understand. Okay, so let's say I have 140 milliequivalents of sodium. Okay, that's how many milliosmoles? 140. Right?
I thought you said 140 and then times 2.
Why would I have times 2? No, forget about that.
Um,
I'm trying to explain, he asked how we get these coefficients, right? And so I'm explaining sodium because it's the easiest one to think about. So what's my normal, sodium's about, what, about 140 milliequivalents? How many milliosmoles is that? 140, right? But here's the thing, if my serum sodium is 140, that's 140 positive charges, right? About how many negative charges should I have? Another 140, right, to cancel the positives out. So that's why I have to multiply that by 2, because I have to take into account those negative charges, right? Does that make sense? Now, there's something similar going on with BUN and glucose, okay? I'm taking into account the units that these are measured in. These are measured not in milliequivalents per liter, but these are measured in milligrams per deciliter. So these coefficients are taking that into account. Does that kind of make a little better sense? And I could go through exactly how we do the BUN and glucose, but it would involve taking glucose is C6H12O6, and we have to look at the individual atoms, get the atomic mass units, find out what each mole, 1 mole of glucose weighs, and then divide it down. But we could get there. It'd be really long and redundant, but at least as my explanation made sense. All right. Okay, cool. All right, so let's go ahead and plug and chug now. So all these are added up. Let's go ahead and just plug in the values that I gave you guys. So what was our patient's sodium? 144. What was the patient's BUN?
15.
15, all right. And what was the patient's glucose?
122.
122. Okay, so what's 144 times 2?
288.
288. Plus, what's 15 divided by 2.8?
Calculator involvement.
All those calculators out easy. I don't even know the answer yet to that question, so we'll find
5.35.
5, what's that?
5.35.
Yeah, that's about right. 5.4, let's just round it up. How does that sound? And glucose, what's 122 divided by 18?
6.7.
6.7. All right, so add 288 to 5.4 to 6.7. Add them up.
300.13.
Yeah, so 300. We'll say 300. So our calculated osmolality is 300 milliosmoles per liter, per kilogram. We know there's a difference, but we're gonna kind of forget that for now. Okay, so that's my calculated what was actual, what was actually measured.
Yours equals 380.
380. 380. So right away we notice a problem. The measured osmolality is a heck of a lot higher than the calculated. Would you guys agree?
Yes.
So the difference is 80 milliosmoles per liter, right? So what does that mean? Well, that means that there's a mystery meat, just like the anion gap that we talked about. An elevated anion gap is a mystery meat, but it is a mystery anion, right? It's something that is adding ghost anions to the plasma. Well, the elevated osmolol gap, there is a mystery meat substance that isn't sodium or chloride, because that's really sodium. When you look at sodium, you're also taking into account chloride and bicarbonate, negative charge stuff. It isn't the urea, it isn't glucose, it's something else. Yeah, it's some other mystery meat. It's often, when these gaps are really elevated, it's often going to be one of the alcohols. There are three major alcohols that we worry about. There's ethanol, there's ethylene glycol, there's methanol, and propylene glycol occasionally run into it. Okay, so 4 of the alcohols. 3 of them are considered toxic alcohols. Even though ethanol is toxic, it's just not as toxic, if you will. Does that make sense? So that mystery meat, if we were to add that mystery meat in there, that should take into account that gap, right?
But your ethanol was 0.
My ethanol was 0. So what I did is I told you, well, we ran the ethanol. So ethanol ain't the mystery meat, is it? There's another mystery meat floating around. So in this case, if you saw this guy and you saw the labs, okay, and you saw that the ethanol is 0, you'd have to consider what? You have to consider, is it ethylene glycol? Is it methanol? Is it propylene glycol, right? So the osmolol gap is a way that can help us identify certain types of toxicity. Now, it's not definitive. It has its flaws, okay? You would never use it by itself to make the diagnosis. But let's say you had somebody and things just weren't adding up on this patient, and because often the anion gap is going to be elevated too. In fact, I would, almost every case, if your anion gap is really high, your osmolol gap is probably going to be high as well, because we know that lots of things that add anions are going to add to the osmolality as well. But let's say that you run through and you're looking, you're like, well, it's not aspirin, the patient's not DKA. Let's see here, the serum lactate's normal. I don't know what's going on. What the heck? Let's just do the osmolol gap, right? You're lost. You don't know what's going on. And then you have this big old osmolol gap, and you go, oh, maybe this guy drank a gallon of antifreeze or something like that. So it's just a tool. It's another tool that can help you when you're kind of like, I don't know what's going on here. Okay. That's why it was an optional thing for your quiz.
Was done.
Did you guys interpret the ABG okay, though? That part was not so optional.
Partially compensated metabolic acidosis.
Yes. Partially compensated metabolic acidosis. What was the anion gap elevated?
Yes.
Yes, you had an elevated anion gap as well. Boom. All right, guys. That's that. So turn your stuff in.